Okay, so we were discussing about concepts related to subgroups, right? Yeah, so in the previous lecture, we had already discussed about what centralizers, normalizers, and center of a group are. Let's introduce two very important subgroups which are related to group actions. Okay, so I've already discussed a lot about group actions in much details. You can go to my playlist on important topics in group theory, and there you can find the related videos on group actions. Okay, so yeah, let's talk about what a stabilizer is. Okay, so before that, let me just quickly introduce the concept of a group action for the sake of completeness. So what we start with is we have a group G, we have a group G, and we have an arbitrary set A. Okay, obviously the set A is non-empty to be precise. Then a group action, we say that G acts on A. Okay, so this is saying G acts on A. So this is equivalent to saying that there is a map. There is a map from G cross A to A. Okay, and the map obeys certain properties. What are the properties? Property number one, that the identity element along with any arbitrary element of A. Okay, let me use the usual notation. Okay, that will be more precise. So the map is some sort of, we write it as so GA, we say is mapped to G dot A. Okay, so this is precisely the notation we are going to use. And so this you can think of it as meaning that the element G acting on the element A. Okay, so what are the conditions? Conditions is that one acts on A to give A. Okay, and this happens for all elements A in capital A. Number two is that the acting of elements from G is a sort of associative. That is, if you take composition of two elements in G, G1, G2 acting on A, so that is same as G1 acting on the element G2 acting on A. Okay, so this is precisely what a group action is. Let me just re-say what I'm telling. That so we start with a group. We have a set. Then we say that G is acts on A if there exists a map from G cross A to A such that the pair GA is mapped to something which we denote as G dot A, or you can say G times A, whatever. And this map obeys certain properties, that is 1 dot A is A and G1 G2 dot A is same as G1 dot G2 dot A. Okay, so this is precisely what a group action is. Um, Now we are concerned about defining a very important subgroups which is quite related to group actions, which is called the stabilizer. Okay, so a stabilizer of a group action. Okay, the stabilizer of a group action. So how do we define it? Precisely, let us start with the group action first. So let one sec, huh? One sec. Okay, yeah. So let G be acting on it. Okay, so let G acts on it. Okay, and let us fix an element from capital. Then we define what we call the stabilizer of A for this group action. Then the stabilizer of A in the action, or you can simply say the stabilizer of A denoted as. So it has a number of notations. We'll rather use the notation GA because whenever we will be talking about stabilizer, I guess it will be quite obvious to have the group action already in hand, right? We will obviously have the group action already in hand. So I guess it should be quite obvious. So the group action is defined as yeah. So that then the stabilizer of A in is it is usually denoted like, we will denote it like this. So it is defined as all the elements in G which fix A upon acting. So G acts on A to give A. That's it. That's the definition of a stabilizer. Okay. Okay. So our claim is that this stabilizer also forms a subgroup of G. Okay. So let me simply write claim. Or okay, before moving on to claim, let me first give a you know an example for a better understanding. Consider D8. Okay. Example. Consider the vertices of D8. Sorry, they consider the vertices of a regular square. Okay, consider the vertices of a regular square, uh, and let D8 act on the set. Okay, this will obviously give you a certain notion about what a group action typically is as well. So a group action in a very simple sense is basically, what is a group? It's a certain structure defined on a certain set. So if you consider the set, or the rather I should say the group, as a tool which helps in arranging and dearranging certain elements in a set, you can think of think of group action in this sort. So group acting on a set A is sort of the structure of the group. The structure is imposing certain uh, modifications in the set A. Typically, that's the fact. Okay. So what are we trying to do here is that, if I explain this in very simple language, so we are starting with the vertices of a regular square. Okay. So suppose we have, okay, so these are the vertices of a regular square. Suppose we name them as A, B, C, and D. And what are we trying to do is that we are trying to make this group D8 act on these four vertices. Now, what does D8 do? So D8 is the, if you remember the definition of D8, so it's the set of all rotations and reflections, maintaining symmetry of a regular n-sided polygon. Okay, of a regular n-sided polygon. So acting D8 on this is basically, it will give you all the possible orientations you can achieve out of a square if you make its vertices rotate, and the square reflect about certain given axis while maintaining symmetry. Okay, for example, if you start with the vertex A, let's say, if you start with this A and you pick the element, let's say R square. Okay, now R to the power 4 must be 1 typically. So each rotation will give you a 90-degree rotation typically. Okay, so every rotational element in D8 will ensure a 90-degree rotation. Because if you start with A, the identity element of D8 will simply mean that is one acting on A. So we start with A. Let me just be a bit precise about it. So what will be 1 dot A? So it means, so it will be A. That is, there is no rotation or deflection acting on it. That is a simple thing. What is R dot A? So R dot A in simple sense is R acting on A. That is, we are, applying the rotation R, the rotation denoted by the element R on A. What does the rotation here typically do? It rotates A by, say, 90-degree anti-clockwise. So we take A to C. Obviously, then C will go to D, D will go to B, and B will come back to A. So if I impose, so R dot A will be simply C, because A is moving to C. Similarly, R square dot A, so we are rotating A twice by 90 degrees, so A will directly go to D, and anti-clockwise we are speaking of. Similarly, R cube dot A will make A go to B, right? And then R to the power 4 will bring A back to A, so it's the identity rotation. I guess now the sense is clear of what a group action typically means. Whatever, I want to say that, what should be the stabilizer of of any of the vertex? My question is um what is the stabilizer, for this action on any vertex? Okay, any vertex, any random vertex you choose, what should be the stabilizer of that vertex? Now it's quite obvious that the action is choosing a single element from D8. So let it be denoted as say X. X is an element in D8. You act X to some element A from one of these vertices. So let it be denoted as V. So you act X to one of the vertices V, and you want that V remains V. That is the thing. So observe, none of the rotations will work because R will move any vertex, R squared will also move any vertex, R cube will also move any vertex. We want to find a certain element from D8 which, when acted upon any of the vertex, will fix it. That is, the vertex remains there. If you carefully observe, that is only achieved by the reflection about the line of symmetry which passes through that vertex. That is, suppose you choose A. Then if you carefully observe that this line of symmetry, if you choose, now this is obviously there are, so you have this as a line of symmetry, right? You have this as a line of symmetry. Let me just start up. Yeah. So you have, see, observe that you have this as a line of symmetry, you have this as a line of symmetry, then you have this as a line of symmetry, and you have this as a line of symmetry. So any vertex you choose, there is a line of symmetry passing through that vertex. So if you choose A or D, there is a line of symmetry passing through that vertex. If this symmetry, the symmetry which which represents the element of D8 which represents this very reflection of the of the vertices about this line of symmetry, then if you make that element act with A will undergo no change, right? Because A won't undergo any reflection about this symmetry. The only elements which will undergo reflection about this line of symmetry is B and C. So suppose this line of symmetry is represented by the element, say, you know, whatever, say Y. Okay. I'm avoiding the notations R and S. Let it be Y. Clear? So Y acting upon A will fix A because A won't go any A won't lose its position when a symmetry is observed about this line of symmetry. Right? Similarly, Y dot D will be D. If you consider now this line of symmetry, then the element which represents this line of symmetry, if acted upon on B and C, acted to B and C, it will fix B and C, right? So what is the stabilizer for this action on any vertex? So it will be the line of symmetry passing through the respective vertex. So this should be the the line of symmetry passing through the vertices. Clear? That is the stabilizer for this vertex A should be this line. The stabilizer for this vertex D should be this line. For B it should be this line. For C it should be this line. I guess it's clear now. Clear? Okay. Okay. Now our claim is that this the stabilizer is a subgroup of G. Okay. So so claim. Okay. Let G be acting upon A. Then for all small a in capital A, the stabilizer of A is a subgroup of G. Okay, so this is what we want to prove. First thing first, G of A is non-empty. Why? 1 is obviously in G of A because 1 will fix every element of A. Okay, so 1 is surely in G of A. Okay, that is the first point to observe. Okay, what more can we say? Let's choose two elements from G of A. Okay, so we will obviously use the subgroup criteria. So let X be in G of A, Y be in G of A. We need to show that X, Y inverse is in G of A. Okay, observe that first thing first, if Y dot A is A, then what can we say about the inverse of Y? See, 1 dot A is okay. Okay, let me rephrase this in this manner. It will be better to understand. See, we have that 1 dot A is A, for all A in A. We can write 1 dot A as y inverse y dot A is equals to A for all A in A. So this implies y inverse dot y dot A is A for all A in A. Okay. Now if y is in A, if y is in G of A, so that implies y dot A is A for all A in A. So if y dot A is A, then we can put it here. So that implies y inverse dot A is A for all A in A, right? So that implies that if y is in A, then y inverse is also in A. Okay. Now we have already shown that the inverse is, the inverses of every element exists. So I guess it's sufficient to show the closure property only. What can I say about x y dot A? If x and y are both in G of A, then x y of dot A by the definition of a group action is x dot y dot A, but y dot A is A since y is in G of A, so it's x dot A. But x dot A is again A because x is in the stabilizer, so it's A. So x y also fixes A. So that implies x y is also in G of A. I guess it's clear. So therefore, G of A is a subgroup of G. Clear? Okay, one sec. Okay. So now let's introduce one more such structure. We call it the kernel of a group action. We call it the kernel of a group action. Okay. So it's kind of similar to stabilizer. So let G be acting on A. We define the kernel of this action as, so it's the set of elements G in capital G such that, you know, so it fixes A. Yeah, it fixes A for all A in capital A. Clear? It fixes A for all A in capital A. So you can, obviously observe that it's indeed a subgroup of the stabilizer of any subset, right? It's sort of similar to what we had in the case of centralizers and centers. So centralizers were set specific, centers were not. Their definition being quite same, or at least their objective being quite same, right? Now, if you recall that there is a very specific and a very important group action as well, which is a group acting on itself by conjugation. Or if I should do not restrict a group acting on itself, I can say that a group action by conjugation, to be precise. Like there were two actions which were, which I have also covered in great details and which are quite important as well, which are group actions by left multiplication and the group action by conjugation. So here what we're trying to do is that we are trying to relate the concepts of stabilizers and the concepts of the kernel using using a very specific group action, which is action by conjugation. Now, if you recall what a group action by conjugation was, I guess you will be quite a bit able to relate the commutativity and the group action by conjugation in the definitions of a stabilizer and a kernel. Okay, let's start. So what we do is that we fix a group, or rather I should say we choose a group. Let G be a group. Let G be a group, and let A be the power set of G. Okay. Let A be the power set of G. Let G be acting on A by conjugation. So if you quickly recall what action by conjugation is, so it's G acting on A as G inverse. Here these elements A are subsets of G, right? Then observe that for any subset you choose of G, therefore for all subset you choose of G, what is the uh, stabilizer of A? So this set of elements G in G by definition such that G dot A is A. But if I apply the apply the definition of action by conjugation, G dot A is nothing but G inverse equal to A. But this is nothing but the normalizer of A in G, right? Right? I guess now you are, being able to get the relation between normalizer and a group action. Quite a bit, I should say. Uh, you know, Almost every important aspect of studying a group can be related to a group action, to a very specific group action. Okay. Now what we do is that now suppose we act, the normalizer of A in G on A. Okay, where A is a subset of G precisely. Okay, clear? Then what is the centralizer of A? I should say what is the kernel of this action. So it's the set of elements G in Ng A such that G dot A is A for all A in for all A in G, right? Sorry, for all A in A, right? So A is given here. Observe that this is nothing but the centralizer of A in G, right? This is the centralizer of A in G because G dot A is G inverse. We have already proved that if G acts on A, then the kernel of the action is a subgroup of G. That, okay, we have not proved it. We have proved the stabilizer to be a subgroup, but you can obviously quite relate the proofs, right? This comes out, that implies, so this readily implies that the centralizer of A is a subgroup of the normalizer of A in G, right? What if I act G on itself by conjugation? By conjugation and ask for its kernel. So the kernel is the set of elements G in G such that G dot A is A for all A in G in this case. But G dot A in G is nothing but G inverse. So we place G inverse on the right. So it's AG. That means it is the set of all elements which commute with every element in G for all A in G. That's precisely the center of G. Clear? Okay. So that was quite a great topic to study. Okay. Now, okay, I won't be starting this lecture here. I will start this topic in the next lecture, which is the subgroups generated by subsets of a group. Okay. Subgroups generated by subsets of a group. And then we will move on to a very specific part of it, which is called the cyclic groups. Now, this part is often ignored a bit while in a very introductory course in group theory. But this topic is of great importance when you will be going for your future studies. So we will start with this topic and then we will be moving on to the cyclic groups as a very specific case of this. Okay. And this will be a topic for our next lecture. So meet you guys in the next lecture.